If you read a blockchain tutorial written before 2024, it probably explained the technology using the analogy of a shared Google Doc or a chain of digital blocks. While fundamentally true, that explanation is dangerously outdated for understanding how modern Web3 actually operates. Early blockchains were like early computers, single, massive mainframes trying to do every calculation, store every file, and route every message simultaneously. In 2026, blockchain architecture has been completely dismantled and rebuilt into specialized, hyper-efficient layers. This guide provides a complete technical overview of how blockchain works today. We will briefly cover the foundational cryptography, but the primary focus will be on the modular stack, the four independent layers of execution, settlement, consensus, and data availability that power the modern decentralized economy. The foundational primitives, state and cryptography. Before we look at the modern architecture, we must understand what a blockchain fundamentally is: a state machine secured by cryptography. State is simply the current snapshot of all balances and data on the network. Address A has 10 tokens, address B has 5 tokens. When A sends 2 tokens to B, the network undergoes a state transition. The new state is A8, B7. To ensure nobody can fake a state transition, the network uses cryptographic hashing, specifically algorithms like SHA-256 or CATEC. A hash function takes any amount of data, a single transaction or an entire library of books, and mathematically crushes it down into a fixed-length string of random-looking characters. If you change even a single comma in the original data, the resulting hash changes completely. Miners or validators bundle thousands of these transactions into a block. They hash all the data in block 1. When they build block 2, they include the hash of block 1 inside it. This permanently links the blocks together. If a hacker tries to rewrite a transaction in block 1, the hash of block 1 changes. Because block 2 contains the old hash, the math breaks, the chain fractures, and the network immediately rejects the hacker's altered timeline. This is the root of blockchain immutability. The monolithic bottleneck. For the first decade of crypto, networks like Bitcoin and early Ethereum were monolithic. A monolithic blockchain forces every single node, computer, on the network to do 4 things simultaneously. 1. Execute the transaction. 2. Agree on the order of transactions. 3. Resolve disputes. 4. Download and store all the data. This is a catastrophic bottleneck. If every computer must process every single trade globally, the network can only ever be as fast as its slowest computer. If you force the network to go faster by increasing the block size, the data becomes so heavy that normal people can no longer afford the hard drives to run nodes. The network becomes centralized in corporate server farms, defeating the entire purpose of Web3. To solve this, the industry shifted to modular architecture. The 2026 paradigm, the modular blockchain stack. In 2026, we no longer build monolithic chains, we build modular stacks. We have decoupled the 4 core responsibilities of a blockchain so they can scale independently. 1. The execution layer, the engine. This is where the actual computation happens. When you swap USDC for ETH, the execution layer processes the smart contract math and updates your wallet balance. Today, 95% of retail execution does not happen on Ethereum mainnet. It happens on layer 2 rollups like Arbitrum or Base, or specialized app chains. These execution environments are designed purely for speed, processing thousands of transactions per second because they don't have to worry about the heavy lifting of global consensus. 2. The settlement layer, the Supreme Court execution layers are fast, but they are just isolated environments. The settlement layer acts as the ultimate anchor of truth and dispute resolution. Rollups periodically take thousands of their executed transactions, compress them into a single mathematical proof, and post them down to the settlement layer, typically Ethereum. If a rollup tries to process a fraudulent transaction, the settlement layer's smart contracts will detect the invalid math, reject the batch, and penalize the rollup operators. 3. The consensus layer, the timekeeper. Consensus is the mechanism that orders the blocks. As discussed in our previous validation guide, this is where proof of stake or proof of work comes in. The consensus layer's only job is to look at the blocks being proposed and get the globally distributed network of nodes to agree. Yes, block 45 strictly happened before block 46. It does not care what the transactions are. It only cares about their strict chronological order. 4. The data availability layer, the public ledger. This is the most critical innovation of the 2026 market. If an execution layer processes 1 million trades and posts a compressed proof to the settlement layer, how do we know they aren't hiding the transaction details? If the data isn't publicly available, nobody can verify the math. Specialized data availability (DA) networks like Celestia or EigenDA have emerged. Their sole purpose is to serve as massive, decentralized bulletin boards. They use advanced cryptography called data availability sampling to guarantee that every single byte of transaction data has been published and can be downloaded by anyone, without forcing every node to store petabytes of history. Parallelization, the next leap in execution. Even with modular architecture, traditional execution layers have a flaw. They process transactions sequentially. Imagine a grocery store with 100 customers but only one checkout lane. That is the standard Ethereum virtual machine, EVM. If someone is buying a complex NFT, everyone else buying stablecoins has to wait in line behind them. Modern execution environments, popularized by networks like Solana and the newer parallel EVMs like Monad, operate differently. They act like a grocery store with 50 checkout lanes. The network analyzes the incoming transactions and realizes that the NFT trade and the stablecoin swaps do not overlap. They touch completely different smart contracts. Therefore, the network's validators process them simultaneously, in parallel, across multiple CPU threads. This architecture is what pushes modern blockchain throughput from hundreds of transactions per second to tens of thousands. Zero-knowledge proofs, the ultimate scaling tool. You cannot understand modern blockchain architecture without understanding zero-knowledge ZK cryptography. Historically, to prove that a transaction was valid, every node had to rerun the exact same math. ZK cryptography replaces re-execution with mathematical verification. A ZK rollup, an advanced execution layer, can process 10,000 complex trades off-chain. Instead of sending all 10,000 trades to the settlement layer for verification, a prover runs a heavy cryptographic algorithm to generate a validity proof. This proof is a tiny, fixed-size piece of data. The magic of a zero-knowledge proof is that it guarantees, with absolute mathematical certainty, that all 10,000 trades were executed correctly according to the rules of the smart contract. The settlement layer only has to verify this tiny proof, which takes a fraction of a millisecond. ZK technology breaks the correlation between computation and verification cost. It allows blockchains to scale infinitely without increasing the hardware burden on the nodes securing the network. Conclusion: a blockchain in 2026 is no longer a single, cumbersome piece of software. It is a highly optimized, modular supply chain. Transactions are processed in high-speed, parallel execution layers. The raw data is dumped onto specialized data availability networks. The chronological ordering is secured by dedicated consensus mechanisms. And the final, immutable truth is locked into a highly secure settlement layer using zero-knowledge cryptography. Understanding this stack separates the tourists from the builders. When a new protocol claims to be the fastest blockchain in the world, you now know exactly which layer they optimized, and more importantly, which layer they compromised to achieve it.